Grade 11s, we're going to go through question 4 now. So this is a chemical equilibrium question. You're given the equation for the reaction that forms hydrogen cyanide, HCN, by reacting methane, oxygen, and ammonia. So we've got our chemical reaction that exists as dynamic chemical equilibrium. First question is to define dynamic chemical equilibrium. Definitions, as always, please go find them in your notes. It refers to a reversible reaction in which the forward and reverse reactions are taking place at the same rate. And if the forward and reverse reactions are taking place at the same rate, then hence the concentrations of the reactants and products remain constant. So if you didn't know that definition, that may make doing the rest of this whole question a little bit harder. So that was the definition. 4.2, explain why a closed container is needed for dynamic chemical equilibrium to be established. You have to have a closed system so that matter and mass are conserved. So no matter can leave the system, because if matter leaves the system, then the concentrations will change. The concentrations won't remain constant and you won't have an equilibrium. So energy or heat can escape. So if you've got a chemical reaction that produces heat, heat can leave the system. If you put your hand on the side of the container, you may feel heat if it's an exothermic reaction. So energy in the form of heat can escape, but no reactants or products, so no matter or mass can escape. We used an analogy at the start of teaching you guys about chemical equilibrium, which was the phase equilibrium. So please don't say that it's not only required for a liquid and a gas to be in equilibrium, so a liquid condensing, a gas condensing to form a liquid or a liquid evaporating to form a gas. That's one example, but it's not only that, and many of you related it specifically to that, which is wrong because that's just one of many examples of an equilibrium. Also the water example with water evaporating to form a gas and the gas condensing to form a liquid, that's an example of a phase equilibrium, a physical phase state equilibrium. It's not a chemical reaction. No chemical change is taking place when the water evaporates or the water condenses. It's just a physical state. That was to introduce you to chemical equilibrium. So with chemical equilibrium, that's when you've then got reactants that react together to form products and products that break down again to form your reactants. So please don't mix that up. Right, the Chatelier's principle, again, basically a definition, essentially. You have to know how to state that. When an external stress, change in pressure, temperature, or concentration is applied to a system in dynamic chemical equilibrium, the equilibrium point will shift in such a way as to counteract the stress. What's a catalyst? It's a substance that increases the rate of a chemical reaction, but it remains unchanged, and a lot of you left out this part, at the end of the chemical reaction. You can't just say it remains unchanged. When? At the start, the middle, the end. You have to explain when it remains unchanged, and the answer for that is at the end of the chemical reaction. So please learn your definitions. I don't know how many times we've told you this. Then you were given a graph and asked to redraw it. I gave you the actual size so that some of you don't draw a teeny tiny little microscopic graph that is 2 centimeters by 2 centimeters, that it would be a reasonable size. Then you had to sketch 2 Maxwell Boltzmann distribution graphs for the reaction taking place at the 2 temperatures. So the 2 temperatures that we were given were 150 and 250. So 150 was T1 and 250 was T2. I'm going to do the 150 in T1 as blue because that's a colder temperature, and the 250 in red because that's a warmer temperature, higher temperature. So we've got T1 and T2. So this basically asks you to redraw the same graph that's in your notes. You didn't even have to give axis titles because those were given. So for T1, which is the lower temperature, the number of molecules that you've got is going to have a lower average energy. So if you think of an exam and everyone, the whole grade writes the exam, and I plotted your percentage against the number of students against your percentage, you'd get a bell curve. So that means that very few learners get very low marks, very few learners get very high marks. Most learners get marks that are somewhere in between, in the middle of the bell curve. So in the middle, that peak, that represents the average mark of the grade. So it's a similar kind of thing when we're talking about Maxwell-Boltzmann distribution. We're looking at the number of molecules and how much energy those molecules have got. Okay. And T1 looks like that. So this point here would be the average molecular energy, because we're looking at molecular energy on the x-axis. That's the average molecular energy. So a number of molecules on the left. So we've got an amount of molecules, and this shows you their energy. Like I said, the peak represents the average. Label your graph so that I know what you are doing, which curve is which. If you don't label it, I don't know what you're doing. And for T2, you're going to have a lower kinetic energy. So the peak for T2 must be lower than for T1. So here, this peak must be lower for T2 than for T1. And after that, then the T2 graph must be higher because your molecules are warmer, higher temperature, and if it's at a higher temperature, they're going to have more energy. Okay. Then you also have to represent the activation energy on the graph for an uncatalyzed reaction at first. And so this is activation energy for the uncatalyzed reaction. And let's just put a little note here that EA represents activation energy. So that's EA for the uncatalyzed reaction. What other labels did you need? So you got a mark for showing T1, a mark for showing T2. You've got a mark for showing the activation energy for the uncatalyzed reaction. And that was 3 marks. And if the energy of T2 was greater than T1, so in other words, sorry, the other way around. So in other words, if this peak was greater than that peak, so T1's peak was greater than T2's peak, then you also got a mark. So that was where the 4th mark came from. Okay, on your graph, then for question 4.4.4, you have to add a catalyst. No, sorry, I've skipped a question. 4.4.3, indicate on your graph how the platinum catalyst affects the reactions at both temperatures. So now I'm going to do this in purple. So you have to show what will happen with a catalyst. So a catalyst, in the previous definition, it says it's a substance that remains unchanged at the chemical reaction. How does a catalyst work? It works by lowering the activation energy. So if your activation energy was, my apologies, if your activation energy was where the black line is, it needs to be lower. So this is increasing molecular energy as you're going from left to right, just like any graph axis works. So you need to show then that the activation energy for the catalyzed reaction will be lower. So then you can call this EA, I'm going to call it EA star, and then make a note on the side that EA star So EA star is the activation energy for the catalyzed reaction. And EA, just EA without the star, is the activation energy for the uncatalyzed reaction. So please make sure that everything is labeled properly. Okay, so that was 2 marks for 4.4.3. 4.4.4, Jack thinks that the addition of a platinum catalyst will result in more HCN being made. Is he correct? No. Guys, a catalyst does not make more of a substance. It's got no effect on the yield. All that a catalyst does is that it speeds up the rate of both the forward and the reverse reactions equally. So it makes the forward and reverse reaction happen faster. It doesn't mean that you're going to get more. If you get 10 grams, for example, of hydrogen cyanide without a catalyst, you're still going to get 10 grams with a catalyst. You're just going to get that product sooner, faster. So you needed to say he's incorrect. Please also don't say, like, a lot of you forgot to actually say that statement. He is incorrect, or no, he's not correct. The amount of HCN produced will be the same. It's just produced sooner because the equilibrium is reached faster. The rates of the forward and reverse reactions are sped up equally. You don't get more substance. Okay, now we have a rates graph. As the reaction progresses, the concentration of all substances is measured as a function of time, and a rates graph is produced. To redraw the following graph. So you had the axis already. Over here, you had to provide the units. The units were moles per decimeter cubed per second. Moles per decimeter cubed per second. Again, from your notes, label the dashed line and the solid line, and this is where things went terribly, terribly wrong. A rates graph represents the rate of the forward reaction and the reverse reaction. Please, so many of you told me that it was for products and reactants. No, it's not. The lines do not represent products and reactants. They represent the rate of the forward reaction and the reverse reaction. So at the start of a reaction, the reverse reaction hasn't yet occurred, because you need to first make some product before that product can break down and form reactant, if you're talking about going from left to right. So at the start of a reaction, you've got lots of reactants, and if you've got lots of reactants, then the collisions between the reactants are going to occur really quickly, and that then means that the rate of the forward reaction is going to start off at a high rate. So the dashed line then represents rate of the forward reaction. Okay. If that's the rate of the forward reaction, then this is the rate of the reverse reaction. Okay. So there's the forward reaction and the reverse reaction. Then you need to read what's going to happen. On your graph, draw what happens between time A and B once equilibrium has been established. If equilibrium has been established, according to your definition of chemical equilibrium, the rate of the forward reaction will equal the rate of the reverse reaction. They're going to occur at the same rate. So if they are now occurring at a constant rate, they're going to continue from A to B. They're going to continue occurring at the same rate. So you just need to draw a horizontal line, flat horizontal line, for both of them. And the lines are actually going to be on top of each other because the rates are equal. So that's what happens between time A and B. That was question 4.5.3. Then 4.5.4. Platinum's added to the reaction at time B. So you're adding the catalyst at time B. And the reaction reaches equilibrium again at time C. On your graph, indicate what happens between time B and C. So a catalyst increases the rate of the reaction. I told you it increases the rate of the forward and the reverse reactions equally. So both reactions are going to have a spike, not a gentle curve, because a catalyst is going to make the rates jump up very quickly. So at time B, you're adding the catalyst, so the rate of the forward reaction, the blue line, increases, and the rate of the green line increases, and they increase by the same amount. So you add your catalyst, both reactions start occurring much faster, so the rates increase, that's why you get a spike, and chemical equilibrium is re-established. So the lines are going to be flat horizontal lines again, they're just going to be occurring at a faster rate. There we go, chemical equilibrium for the reverse reaction and chemical equilibrium. And for the forward and reverse reaction, same rate because the lines are on top of each other. So you've got a mark for the spike, so that spike, that they both the forward and reverse reactions jumped up, and then a mark for showing that both the forward and the reverse reactions are occurring at equilibrium. So these lines are on top of each other, the blue and the green lines are on top of each other. If you messed up your labels, then this whole graph is wrong and therefore meaningless. So if you told me that this was reactants or products and this was products or reactants, lies, rubbish. It means that everything else is going to be wrong, and that's why you didn't get any further marks. So please make sure you know what the values, the lines on a rates graph represent. Okay. 455, there are 3 reactants in the chemical equilibrium that you were given, the Andrussow process. However, there are only 2 lines on the graph. Is this correct? Yes, it is correct, because it's a rates graph, and on a rates graph you only have 2 variables, the rate of the forward reaction and the rate of the reverse reaction. So it doesn't matter, you could have 100 different products or 100 different reactants for a chemical reaction. You're still only going to have a rate of the forward reaction and a rate of a reverse reaction. So a chemical equilibrium reaction has only got 2 rates, the forward rate and the reverse rate. So yes, the graph is correct. Get a mark for saying yes, it is correct. and then you needed to say that a rates graph should only have two lines for the rate of the forward reaction and the rate of the reverse reaction, not products and reactants. So many of you did that wrong. You said that it was for the rate of the reactants or the rate of the products. No, it's the rate of the forward and reverse. Or some people said that the one line represented reactants or represented products. Again, lies, rubbish. Go away, hardy dies. 4.5.6, Jack says that after time C, since there's no change in the concentration of the reactants, it means that the limiting reagent has been used up and the reaction's gone to completion. Explain two flaws in his logic. So a reaction that's happening in equilibrium, a dynamic equilibrium reaction, doesn't go to completion. That's the point of it. So it never ends. As reactants combine to form products, those same products break down for the reverse reaction to form reactants again. And so the reaction will continue forever. There is no limiting reagent in a chemical reaction that's at equilibrium. So the reaction's not gone to completion because the reaction's in equilibrium. The limiting reagent hasn't been used up because the forward and reverse reactions are happening at an equal rate. As something is being used to make a product, as a reactant is being used to make a product, that same product breaks down again and forms more reactant. So the rates for the forward and reverse reaction remain constant. Okay, so that was question 4. Let's go on to question 5. I apologize for the tapping in the previous video. I didn't have my headphones in, so I was using the tablet's microphone, which also picked up my pencil that was tapping on the screen. Okay, so question 5. The pirates like the whole chemical equilibrium thing. In another quest to create chemical weapons, Captain Jack Sparrow, leader of the pirate lab, and his crew discover an explosive element, diatomic element, bang, with the symbol B. There was a little disclaimer that bang is not boron. Bang is just a fictitious element, so please don't treat it as boron, but that doesn't have much consequence. Bang can be created by heating AB3, so that AB3 decomposes to form AB2 and B2. And is the chemical reaction balanced? Yes, it is. So you don't need to worry about balancing it. The reaction takes place in a 2 decimeter cubed container. So please make a note that that's going to be your volume. At 500 degrees, that's temperature, so really hot, and it reaches chemical equilibrium after 8 minutes. So we've got a graph. Please make sure you look at the title of the graph. This is a moles graph, so it's an amount versus time graph. How much of a substance have you got? It's not a concentration graph because concentration is measured in moles per decimeter cubed. If you wanted to get the concentration, you'd have to take the amount off this graph, these values off the graph, and divide it by the volume. Concentration equals number of moles per unit volume. So any of these values, if you take, let's say at this point, for example, if you take 4, so the amount of AB3 at 8 minutes is 4 moles. 4 moles in 2 decimeters cubed would be 4 divided by 2, which is only 2 decimeters cubed. So it's not a concentration, it is an amounts graph. Make sure you're aware of that. Before you even start, it's a good idea to do some highlighting. I really recommend you do highlight your graph. Okay, so AB2. Okay, so the orange is AB2. Let's do AB3 in blue. And in yellow we can do the last one, which is B2. So by doing it in color and highlighting the same reactants or products on your chemical equation, it helps you to relate the chemical equation to the graph. Okay. Right, write an expression for the equilibrium constant for this reaction. So the equilibrium constant, Kc, is the ratio between products to reactants. Okay. So, obviously those are our products, and AB3 is the reactant. So for question 5.1, Kc equals to the ratio of products to reactants. So we're going to have AB2 the concentration of AB2, so you have to use square brackets because AB2 is a product, times the concentration of B2 because B2 is our other product. There is a 2 over there, so you need to have a squared over there. Okay, and then the ratio of reactants, the only reactant is AB3, so the concentration of AB3. How many AB3s have we got? 2 AB3s, so you need to square the concentration of AB3 because that's what you do when you're getting Kc. A lot of you left out those, some of you got the inverse of that wrong. Please make sure you know how to get Kc values. They just asked for an expression, so you didn't need to actually do any substitution. Question 5.2, so that's 5.1, there's your Kc expression. Mark for the whole numerator correct, mark for the whole denominator correct. It's question 5.1. Question 5.2, using your answer to question 5.1 and the graph, calculate the value of the equilibrium constant at 500 degrees. So now you actually need values for the concentration of AB2, B2, and AB3 at 500 degrees. When is this reaction taking place at 500 degrees? Between 8 minutes and 16 minutes. And you can see that between 8 and 16 minutes, the concentrations of the reactants and product remain constant because the reaction is at chemical equilibrium. Okay, so we're going to take the value at 8 minutes because that's when the reaction does reach the 500 degrees, although all along it's the same, so wherever you take your value is fine. So we've got 6 as the concentration for AB2, 4 as the concentration for AB3, and so many of you made a silly mistake here. This is 2, and that's 4. Halfway between 2 and 4, oh my goodness, is 3. So many of you decided that that value is 2.5 because you didn't look at the graph correctly and interpret the graph properly. Very silly mistakes. All right, so at time 8 minutes, the concentration for AB2 is, let me actually even color code this for you so it's even more obvious. Concentration for AB2 is 6. So there's AB2, concentration for AB2 is 6. So the formula for concentration, C equals to N over V. We've got 6 moles of AB2 from the graph. The volume was 2 decimeters cubed. And the 6 comes straight from the graph as the concentration of AB2 when the reaction's at equilibrium at 500 degrees between 8 and 16 minutes. Okay, so 6 divided by 2, which is 3. Two is the volume. Units for concentration, you have to give it moles per decimeter cubed. Okay, now let's do our next substance. Let's do the blue substance. AB3, concentration of AB3 at 500 degrees, 4 moles. So the concentration of AB3, C equals N over V. 4 divided by that same volume which was given, it's still a 2 decimeter cubed container. 4 divided by 2 is 2 moles per decimeter cubed. Okay, then our last substance is the yellow one, so B2. And as I showed you, the concentration of B2 at 500 degrees, which is between 8 and 12 minutes, is 3. Halfway between 4 and 2 is 3. 3 moles. So concentration of B2, C equals to N over V. Number of moles I said was 3 moles. The volume is still 2. And 3 over 2 is 1.5 moles per decimeter cubed. Okay, so now we've worked out the concentration of each of these substances. Now we can put it into our Kc value. Okay, so there's Kc. So now we're going to have Kc equals concentration of AB2, so that's the orange substance, which is going to be 3. Note that there's a squared there, so 3 squared times the concentration of B2. B2 was our yellow substance. The concentration of the yellow substance, B2, was 1.5. So 3 squared times 1.5 divided by the concentration of AB3. AB3 was our blue substance, and the concentration of the AB3 was 2 moles per decimeter cubed. And because of that 2 over there, you need to square it. Do the maths, and you come out with 13.5 over 4. And 13.5 over 4 is 3.375. Round off to 2 decimal places, so Kc equals to 3,38. Remember, no units for Kc. Okay, so you've got to mark for the correct number of moles. You have to have your C equals N over V formula 3 times. Once, twice, 3 times. Then you've got to mark for dividing by 2 for the volume. So that's what I've done in red for all of the calculations. Dividing by 2, recognizing that that was the volume. A lot of you forgot to divide by 2. And then, of course, the last mark for the final answer. Something that a lot of you forgot to do is to convert to concentration. So Kc relies on concentration. These square brackets, those square brackets represent concentration. You have to convert to concentration. And if you don't have a concentration graph, if you've got a moles graph like this one, then you need to convert moles to concentration. So moles is N. You need to go C equals N divided by the volume to get a concentration. And once you've got concentration, then you can substitute your concentration values into the Kc expression. So many of you forgot to convert to concentration. You just went ahead and used the values of 6, 4, and 3, which is number of moles, not concentration. You never converted to concentration first. So please look out for that again in future. I did tell you, and I'm sure Ms. Orchard did too, you highlight your graph title, the y-axis of your graph, so that you know what type of graph you've got. 5.3.1 asks, is the forward reaction endo or exothermic? Use Le Chatelier's principle to explain. So the pirates think that if they increase the temperature, they'll get more bang. At the 16th minute, so that happens over here, at the 16th minute, they increase the temperature of the reaction vessel. So at 16 minutes, it gets hotter, heat is added. So increase the temperature, you can think of adding heat. So they add heat at 16 minutes. So now let's have a look. At the 16th minute, just want to tidy this up a little bit. Okay, at the 16th minute, you can see that the blue line increases. So we get more of the blue, more of AB3. Also at the 16th minute, the orange line goes down. Orange line goes down at the 16th minute. Yellow line also goes down at the 16th minute. So what do the orange and the yellow represent? Well, the orange and the yellow represent products. Okay, so at the 16th minute, our products are going down. The amount of product that we've got goes down. The volume is going to stay the same. So if the amount goes down, but the volume stays the same, the concentration decreases. Okay. If the blue line goes up, remember the blue represents reactants, so we're going to get more AB3. If the blue line goes up, then it means that that concentration is increased. Which reaction, the forward or the reverse, would make more blue? Well, the reverse reaction would make more blue. The reverse reaction makes more AB3. Okay, so if the reverse reaction was favored by adding heat, let's write that down quickly. So add heat, or increase the temperature, whichever. Increase the temperature, add heat, favors the reverse reaction. So if the reverse reaction is favored by adding heat, then that must mean that you've got an exothermic reaction. So if you've got an exothermic reaction, you can write plus heat over here. Think of it that way. Don't write it. That's a secret. Don't write down the secret. So if heat is a product and the reverse reaction is favored, why would you favor the reverse reaction? Well, to use up that heat. So there we go, there's heat, reverse reaction favored, use up the heat, reverse reaction makes more blue. You can see that there's more blue by the increase in the amount of blue on the graph. And I hope that all those stories tie together for you. So the forward reaction is exothermic. Increase in temperature favors the reverse reaction. How do you know that the reverse reaction is favored? Because of this increase on your graph of the blue. And the blue is a reactant, so you're making more reactant. Which reaction, forward or reverse, makes more reactant? Reverse reaction makes more reactant. If it was the reverse reaction that was favored by adding heat, then that must mean that you're trying to use up the heat. And if you're trying to use up the heat, then heat has to be a product. And if heat is a product, then it's an exothermic reaction. So that's what you had to say for 5.3. According to Le Chatelier, go away, hardy dies. According to Le Chatelier, because the question did ask you, use Le Chatelier's principle to explain your answer. So you have to make reference to Le Chatelier. According to Le Chatelier, an increase in temperature favors the reaction, which decreases the temperature. So the endothermic reaction. And in this case, it's the endothermic reaction that is favored. In this case, at time 16 minutes, when the temperature is increased, so heat is added, the reverse or the endothermic reaction is favored, the reverse reaction, the endothermic reaction is favored. And if it was the reverse endothermic reaction that's favored and the reverse reaction is endothermic, then it must mean that the forward reaction then is exothermic. So reverse would be endo, forward would be exo. Okay, question 5.3 asks, how does the equilibrium constant between time 8 minutes and 16 minutes, so it's going to be along this red line here. So in the red box, the Kc value, and that's the Kc value that you've already calculated, compared to that between time 24 minutes and 32 minutes. So once equilibrium's been re-established over here. Okay, so that we had the reaction taking place, there was the change, the temperature was increased between time at time 16, and equilibrium was adjusting between time 16 and 24. At time 24, though, you can see that the blue, the orange, and the yellow lines are all flat horizontal lines. That means that the amount of substance remains constant. The volume didn't change either, so that then means amount and volume the same, concentration is the same. So if the concentrations of the substances remains equal, then equilibrium is re-established. Okay, so time 24 minutes to 32 minutes, flat horizontal lines, so equilibrium is re-established again. Let's compare the Kc values, though, between the red time interval and the green time interval, so 8 to 16 versus 24 to 32. So at time 8 to 16, the yellow and the orange went down. You can see the orange was at 6, and the orange went down to a value of just under 2, 1.5 to 2, it went down. Okay. Same applies for the yellow. The yellow was at 3, and the yellow went down to about a half, or 1. Point being, yellow went down, orange went down. So what that actually means is that the yellow and the orange are in the numerator. So if the value for your numerator became smaller, so your numerator value became smaller, so actually if your numerator became smaller, then let's have a look at what would happen to the denominator, because you have to consider both the numerator and the denominator. So the numerator became smaller, and the denominator went from, it had an amount of 4 moles in 2 decimeters cubed to an amount of 8 moles in 2 decimeters cubed. So your denominator then became bigger. If you take a smaller numerator and divide it by a bigger denominator, then your value of Kc would decrease. So whatever the value is that you had for your numerator, it became smaller. So you're dividing a smaller number by a bigger number because the denominator became bigger. A smaller number divided by a bigger number will give you a smaller answer. So a smaller Kc. And they asked, how does the equilibrium constant compare? It would be less than the previous value, less than what was happening between time 8 minutes and 16 minutes. Rigetti, the glass eye guy, suggests that if you squash the container, you are decreasing the volume. If you decrease the volume, you're actually increasing the pressure. So if they do that, then they can get out more bang. At time 32 minutes, the pyrites decrease the volume of the container from 2 decimeters cubed to 1 decimeter cubed. So the volume is halved and they keep the temperature constant. How will each of the following be affected? The reason why you all got a mark for question 5.4.1 is we needed to give you an extension of the graph and to show you what happened after time 32 minutes. So you actually didn't have enough information to do that, so you all did get that mark. The number of moles of AB3. So the number of moles of AB3, you need to use Le Chatelier's principle to explain your answer. So refer to according to Le Chatelier in your answer. So the number of moles of AB3, what would happen if you increase the pressure? If you increase the pressure by decreasing the volume at constant temperature, then you're going to increase the pressure. You needed to state that you would increase the pressure. Okay? And according to Le Chatelier, where's our equation? According to Le Chatelier, have a look at the number of moles of gas on the left. You've got 2 moles of gas on the left, so we've got 2. And on the right-hand side, we've got 2 plus 1. So 2 moles of gas on the left, 3 moles of gas on the right. According to Le Chatelier, if you increase the pressure, then the equilibrium would favor the reaction which produces fewer moles of gas. So if you increase the pressure, which side has got fewer moles? The left-hand side. So that means that the reverse reaction would be favored. If you're favoring the reverse reaction, because the reverse reaction would shift the equilibrium to the side with less moles of gas, the left-hand side with 2 rather than 3 moles of gas, then it would try and reduce the stress. So it would reduce the pressure increase. It would lower the pressure, which is the opposite of what was done, the disturbance that was done to the system, which was to increase the pressure. So in this case, the reverse reaction is favored, and the reverse reaction produces more AB3. So if you're producing more AB3, then the amount or the number of moles of AB3 would increase. So you have to say that the number of moles of AB3 would increase because the volume change, decrease in volume increased the pressure. So squashing the container was a volume change, increase the pressure. If you increase the pressure, then according to Le Chatelier, the stress to the system, meaning the increase in pressure, favors the reaction which produces fewer moles of gas. For this reaction, we've got 2 moles of gas on the left, 3 moles of gas on the right. Reverse reactions favored, and the reverse reaction produces more AB3. Okay. So many of you lost marks because you talk about favoring the side. Do not speak about the side. You have to refer to the reaction. Not favors the side which produces more moles of gas or less moles of gas. It favors the reaction which produces fewer moles of gas or more moles of gas. Please don't ever speak about a side again. Banish side from your vocabulary. Just as for physics, you need to banish deceleration from your vocabulary. But we're not doing physics now. Okay, so that was question 5. Question 6 was about their quest to create chemical weapons. He discovers, Jack Sparrow discovers that hydrogen iodide can be made by reacting hydrogen with iodine. So there's the equation, hydrogen and iodine react to form hydrogen iodide. So here we've got a volume, we've got 0.046 moles of hydrogen, and, sorry, not a volume, an amount. That's our number of moles, an amount. And a number of moles of iodine. They are heated to 623 degrees in a 1,000 centimeter cubed closed container. When you read that, you should feel uneasy. You should want to convert it to decimeters cubed. How do you do that? 1,000 centimeters cubed, divide by 10 3 times. So divide by 10 cubed, in other words, divide by 1,000. So that will give us 1 decimeter cubed. That's our volume. Please make sure you convert. A lot of you lost marks for not converting. So it happens in a closed container. The equilibrium mixture is found to contain 7,49 times 10 to the 3 moles of iodine. That's at equilibrium. Determine the concentration of hydrogen iodide at equilibrium. So this, you need to use the table method to do that. So you're going to write out your chemical equation. I2, going to need to do this a little bit smaller. Okay, so there's your chemical equation at the start of the reaction. This is our starting amounts over here. Okay, so at the start we've got 0.496 of H2, and this is moles of H2, and 0.181 moles of I2 at the start. Have we made any hydrogen iodide at the beginning? No. You're just adding those two reactants. You don't have any hydrogen iodide yet. So you've got 0 at the start. Then they tell us for the reaction, actually they don't tell us too much, but the equilibrium mixture is found to contain this value, 7.49 times 10 to the minus 3 moles of I2, and that's at equilibrium. So we're going to come back to the reaction, but at equilibrium, or at the end, we've got 7.49 times 10 to the minus 3 moles of I2. Okay. And if we've got 7.4 moles of I2 at the end, and you started with 0.181, then that means you would have had to have made 7.49 times 10 to the minus 3 minus 0.181, and that would give you 0.174. So 7.49 times 10 to the minus 3, what you ended with minus what you started with, will give you what you made. Now look at the balancing numbers. First of all, is the equation even balanced? You should have checked that at the very beginning, my bad. I should have told you to check that this equation that you were given is balanced. Is it balanced? 2 iodines, 2 iodines, 2 hydrogens, 2 hydrogens. Yes, it is balanced. Wonderful. So it is balanced. So our stoichiometric numbers are 1. 1 is to 1 is to 2. So I've got a 1 is to 1 is to 2 ratio. So if you made 1 mole of iodine, that would have meant that you would have also had to have made 1 mole, the same amount, same ratio of hydrogen. These are moles. And twice as much, because of the 1 to 2 ratio, you would have then made, you would have used 0.174 moles of iodine, you would have used 0.174 moles of hydrogen, and that would have meant that you would have made twice as much because of the 1 to 2 ratio of hydrogen iodide. So 2 times 1.74 gives 0.348. Just to run through that again. So if you started with 0.181, if you start with 0.181 and at the end you had 7.49 times 10 to the minus 3, 7.49 times 10 to the minus 3 minus the 0.181 will give you 0.174. Because of the 1 to 1 ratio, if that's 1.74, this will also be 1.74. And because of the 1 to 2 ratio, this will be twice as much. So the hydrogen iodide will be twice as much. 0.174 times 2 will give you 0.348. And to get this value, if you started with 0.496 moles of hydrogen iodide and you used 0.174, then how much will you have at the end? So 0.496 minus 1.74 gives 0.322 moles of hydrogen. And again, using the divide up, multiply across. So at the end, looking here, let's do that in another color. If you started with 0 moles of hydrogen iodide and you made 0.348 moles, then how much have you got at the end? Well, if you start with nothing and you make 0.348, then you're going to have 0.348 moles of hydrogen iodide. So if you start with nothing, you make 0.348, you're going to have 0.348 at equilibrium or at the end. Just want to put in some lines into this table because it's getting a little bit messy. Okay. And in terms of concentration, so all of these values represent moles. I have even written the units in here for you. They all represent moles, okay? And you should do that too. You should either write moles as your header, as a column header, so that I know that your units are moles, or you can write it each time, up to you. At equilibrium, the concentrations, how do you work out concentration? C is equal to N over V. The concentrations, let's work out what those are going to be. So the concentration is going to be this value divided by the volume. What was the volume? 1 decimeter cubed. So in this case, it was quite nice because even if you didn't divide by the right value, you would have still got the right answer. But we won't always give you a value of 1 decimeter cubed. If this was 2 or 3 decimeters cubed, for example, you would need to divide by that value. So obviously a number divided by 1 will be that same number. So 7.49 times 10 to the minus 3 divided by 1. C equals to N over V. C equals to N over V. And here C is equal to N over V. The V is going to be 1. The V is going to be 1. The V is going to be 1. So 7.49 times 10 to the minus 3 over 1 is of course going to be 7.49 times 10 to the minus 3. And that was actually what was given in any case. They gave us that value over there, but that was in 1 centimeter cubed. So that value divided by 1 is of course that same value. Okay. Then for the hydrogen, we've got 0.322 divided by the volume of 1 will give us 0.322. This is moles per decimeter cubed. You could write your concentration units here if you wanted to. And here your amount was, your number of moles was 0.348. 0.348 divided by 1 is 0.348 units moles per decimeter cubed. And you got a mark for each row. Okay, so that was question 3.4. Sorry, not 3.4, 6.1, question 6.1. Question 7, last little bit. We've got two reactions, reaction 1 and reaction 2. You needed to write increase, decrease, or no change for each of these three in the table below to identify the expected effect of each change on the rate of the forward reaction. Okay. So question 7.1.1, the change was the addition of steam. Now here you have to be really, really careful. You cannot change the concentration of a solid or a liquid because a liquid has got a fixed volume. And in that fixed volume, you've got the same amount of particles. So you can't add or remove particles from water. So you cannot change the concentration of water. However, if you heat water and it becomes a gas, you could have that same number of particles. Say, for example, you've got 50 particles in 1 liter. That would be your concentration. If you then change the volume, you'd still have that same 50 particles in, say, half a liter, for example, which means that your concentration is doubled. So what I'm saying is that for pure liquids and pure solids, you cannot change concentration. However, if you did have a pure substance that is then a gas, for example, water that gets heated and made into steam, gaseous liquid, water vapor, steam, then you can change the concentration. So we're dealing with reaction 1, reaction 1. There we go, reaction 1. We are increasing the concentration of steam, water vapor. If you increase the concentration of steam, that's going to increase the rate of the forward reaction. So if you're increasing the concentration of steam, then you've got more particles, more H2O particles, which can collide with those methane particles. More particles colliding, more frequent collisions, faster rate. So that's why this becomes an increase. Okay. for 7.1.2, if you increase the temperature of any chemical reaction, the particles are going to move faster, more kinetic energy. If the particles are moving faster, you're going to get more collisions. Some of those collisions will be with successful the correct orientation and sufficient kinetic energy. But basically, increased temperature, even in grade 9, you would have learned increase in rate. So increase in rate. And if you add a catalyst, adding a catalyst would also increase the rate of both the forward and the reverse reactions equally. We did that in a previous question. So this would also be increase. Okay. Using the equations provided, write the overall equation for the industrial production of hydrogen, which combines both steps, ignore enthalpy. So all you needed to do is to take both these equations and add them up. So just like you would add simultaneous equations, these are chemical equations, you add them. So CH4, and you learned last year that you always had to include your phases. On the left-hand side of this one, we've got a carbon monoxide. On the right-hand side, we've got a carbon monoxide, so that gets deleted, cancelled. Plus, we've got a water plus a water, gives us two waters, so steams rather, gaseous water. In equilibrium with 3 hydrogens plus 1 hydrogen gives us 4 hydrogens in the gaseous phase, plus 1 carbon dioxide in the gaseous phase. Done, 3 marks. Question 7.3 asks, using your equation above, justify whether this reaction should be carried out at a high pressure or a low pressure. Explain your answer fully. So you need to consider the number of moles of gas on the left versus the number of moles of gas on the right. So for this equation, we've got 1 plus 2, these are all gases, gas, 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 gas. We've got 1 plus 2, which gives us 3 moles of gas on the left, and it's in equilibrium with 4 plus 1, so 5 moles of gas on the right. So if we've got 3 moles of gas on the left and 5 moles of gas on the right, then would you want to carry out the reaction at high or low pressure if you want to try and get your product being hydrogen? So you want to get more of the product on the right. So you want to shift, you want to favor the side which produces, you want the equilibrium to shift so that you're going to get more product. The reaction should be carried out at low pressure, and the reason why is a low pressure favors the reaction which produces more moles of gas, more of your product, more hydrogen, and that's what you want. And in this case, the reaction which produces more of your product would be the forward reaction. So you need to favor the forward reaction. How do you do that? Low pressure. A low pressure shifts equilibrium to the side with low pressure shifts equilibrium to the side with more moles of gas. And in this case, the side with more moles of gas is the right-hand side, so the forward reaction would be favored. So you needed to say the reaction must be carried out at low pressure to get 1 mark. And the reason why is because a low pressure will favor the reaction, according to Chatelier, which produces more moles of gas for your 2nd mark. And in this case, it's the forward reaction that produces the desired product, the hydrogen. So it's the end of the video. I hope that this really helped you. Good idea to please go through your paper and check how many marks you lost due to definitions alone, how many marks you lost due to careless mistakes alone, such as converting units, and silly things like that, and see how your mark would have improved if you added that value to your total marks. Thanks, grade 11s.